Hey everyone, and I'm Prithvi of Electronics and Communication Department, and 94410491 is my student ID, and here goes my continuous alternative assessment 2 of ETC, and my topic here is it's Zephyr biasing techniques. Zephyr stands for Junction Field Effect Transistor. It's same as the biasing of the Zephyr is as same as um, bipolar junction transistor, nothing but the BJT. We'll be having just a second. Yeah. Biasing of Zephyr. We'll be having same biasing techniques for the BJT2. The same are used in Zephyr 2. The fixed DC biasing, self biasing technique, and the potential divider biasing. See, the thing is, we'll be using an external voltage in the first one, fixed DC biasing technique, and we'll be using a resistor instead of an external voltage in these last two biasing techniques. If we look into the fixed DC biasing, um, the external voltage is used, and then we'll be calculating the current from ID. Probably the drain current will be calculated by that, and the VDS, the voltage along the drain and the source is calculated by using the some uh, by using some basic formulas. Obviously, the Ohm's law. By using the Ohm's law, we'll be calculating the VGG is equals to VGS, and that's how it's done. Self biasing technique. We'll be connecting a voltage, a resistor, which is parallel to the source. And when it comes to voltage divider biasing, we'll be connecting one more resistor, which is series with the which is parallel to the source. It's almost same as the self biasing technique, but we'll be using two resistors, which are in parallel, which are in series, but parallel to source. We look into that. The first one is fixed DC biasing technique. This is done by inserting a battery in the gate circuit. The negative terminal of the battery is connected to the gate terminal. As a gate current in ZFIT is almost zero, there will be no voltage drop across the input gate resistance. Hence, the negative potential of the battery directly reaches the gate terminal. The corresponding drain current in drain to source voltage would be the output operating point of the transistor. And as in ZFIT, there is no gate current. We can find the value of the drain current, basically the current through the drain, which is termed as ID. By using the relation, we'll be getting it as IDSS, and the VG of is nothing but the potential VP, or given the transistor data sheet, basically just a second. And this is how the fixed bias JFET circuit looks like. You can see there is no current passing through gate, so that's the advantage. And VGG, the external voltage, will be connecting, and ID is the current passing through drain. So VDD, it's not VDD, it's VDS. The voltage across V, D, and S. Sorry, the voltage along D and S, drain and source. By using this logic on applying KVL, Kirchhoff's voltage law, we have calculated the output voltage. VGS is equals to VGG. VGG is the voltage we supply, the external voltage, and VGS is the voltage. It's done that way. And here's the self-biasing technique. Self-biasing technique is as simple as the initial ZFET circuit, like without an external voltage and all. It just will be connecting a resistor which is parallel to source resistor RS. RC is connected in parallel with RS, and due to this, there is voltage biasing. across D and S as initially in the ZFET, the current along the gate is almost neglected. It's almost zero. So that's the advantage of ZFET. The same thing is done here by applying the voltage, sorry, not voltage, by applying the Ohm's law, we calculate the voltage drop along the R2 resistor, which is RD. So RS is the voltage along source resistor. Sorry, the voltage along the RS would be Vs is equals to ID into RS. ID is the current through the drain, and if we consider the voltage along the gate, it would be zero because there is no current flow through that. And the voltage between gate and source is VGS, which is VGS is equals to VG minus VS. VC is zero, and VS is ID into RS, and we'll be getting it as V is equals to minus ID into RS. And this equation tells us that here the gate terminal always gets negative potential than the source terminal. Um, it is simple like uh, the voltage along gate and source is always negative. Then Vs. I mean, if we consider it as separate, like voltage along the source would be less, which will be greater. Like it will be the positive, and considering VGS, the voltage along the gate and source would be negative. And by using the Ohm's law, we'll be getting the same thing. ID is equals to IDSS of 1 minus G by 1 minus GS by 1 minus VS of whole square. And the equation we got here as VDS equals to VTD minus ID into RD plus RS. And that's a Bessel balancing technique. And the final one, potential divider balancing. This is the final balancing technique which we'll be using, which is almost same as self balancing technique. Have a look here. Like RS is the source voltage, R2 and R1 are the external, sorry, RS is the source resistor. R1 and R2 are the resistors which are parallel to the source. R1 and R2 are in series. And just a second. In this technique, an additional resistor is used and circuit is slightly modified from the balancing technique. Obviously, when we look into that, there is only RG. Now we have added R1, a slight difference. A potential voltage divider using R1 and R2 provide the required DC biasing for the ZFET. The voltage drop across the source resistor is needed to be larger than the resistor divider gate voltage. And the same thing happens here. VGC is always negative. I mean, it stays negative. It remains negative. So the two resistors connected in series form a voltage divider circuit, and the device current flows through the resistance, causes a voltage drop. If this source voltage drop mm, is greater than like is greater than voltage applies at the gate terminal. The thing they want to express is like the voltage drop. The source voltage drop is greater than the same thing. Like VGAG would be negative and VG should be positive. The same thing the same thing is going to happen here. The gate to source voltage has negative value. Gate to source, the VGS is negative, which is desired for ZFET operation. Here's a calculation. VG is equals to VDD into R2. R2 with a one more resistor which is parallel to R1. Sorry, which is in series with R1. And again, V2 is equals to VGS plus ID into RS is equals to VGS is equals to V2 minus ID into RS. And the final one, the current along the drain is ID is equals to V2 minus VGS by RS. by the source resistor, and the VDS is the potential drop along the in the source, and it is VDD minus ID into RD plus RS, and that's a final biasing technique. And we have covered the fixed DC biasing technique, self biasing technique, potential divider biasing technique. Obviously, the potential divider biasing, which is done by using two resistors which are in series with itself and parallel to the source resistor. And that's that. Thank you. Thank you for your attention.